We're going to look at exponential growth and exponential decay problems today. Growth means something increases over time, where decay means something decreases. Um, when you're talking about a car or other new things that you buy, they typically decrease in value over time. One of the few things that does increase over time would be like a home when you buy it. However, it is common for population to increase over time. Now, we have four different equations that we can use. Now, exponential growth would be this or this. Now, if it's more of a scientific situation, you'd use the bottom one with E. If it's not really scientific, I mean, if you're dealing with bacteria and chemistry stuff, you definitely use a highlighted blue one. If it's not scientific, like just what's the population going to be in a certain time or a home growing at a certain rate, it would be the highlighted yellow one. Now, when you're dealing with exponential decay, that means things go down over time. And that would be the green one or the pink one. Once again, if it's more of a scientific one, you would use the one with E, for scientific situations. Now, if you're dealing with something going down in value, then you would want to make sure you're using the highlighted green one. Now, in all of these, A is your initial amount, and Y is your final amount. T is often in years, but not always, but often in years. But you'd have to read in the context of your problem if they're talking minutes or hours or something like that. But T is always some form of time. Now, in the top two that are non-scientific, R is your rate of increase or your rate of decrease. Typically, that'll be given to you as a percentage, but you then need to change it from a percent into a normal decimal by moving your decimal point over 2 spots. When you're dealing with the bottom two that have E, they have the value of K. K is often a relatively small number. If you happen to be dealing with carbon-14 and the half-life of carbon-14, just know that that value of K is always going to be this. So just be aware of that. Now let's go ahead and take a look at a couple of problems. So here we're looking at our power output, and in this case they're giving you the equation. Sometimes they won't give you the equation, you need to select one of those last four to see which one it is. So here they're telling you that we have 100 days, that's going to be our time. So we're going to go ahead and we're trying to find power, so we know that's P. Just plug that in, and we'll have then a negative 100 that we put in up here. And now, since your variable that you're looking for, which is P, is already on one side all by itself, you can just type it into your calculator. You go 50, then your E, which is second ln, and then it might give you a caret key, it might not, but make sure you put that negative 100 divided by 250 in parentheses. And then you type that in and you get your P to be 33.5160, and then you got to figure out what are the units of P, and up here it says that P is in watts. So go ahead and look at the next problem, read through it. Here we're dealing with bacteria growing. I would say then it's probably going to be a scientific one where we have E. We also know that because we have a K, and K does not show up in the ones that just have R. And it starts out at 9, and it grows up to this here. So therefore, we're going to be, whoa, just a second, lost my screen. We're going to be dealing with this one here. So I'm going to write that out. what we're starting out with is your A value, which is just 9. Your K value, they're telling you what that is. And what you're ending up with is that 738. And you're asked to figure out T. So we need to go ahead and get the part with the exponent on it on one side by itself. So that means we'd have to get rid of this timesing by 9. So to get rid of that, you divide. Now, this is not something you can easily do in your head over here, so just leave it as a fraction. Now, since your variable's in the exponent, you need to go ahead and use log. Since we are dealing with e, I'm going to use a natural log to both sides, or you could use your definition of a logarithm. Either way, you would get to the same next step. Natural log of this 738 over 9 is equal to your 0.872t. If you use the definition of a logarithm instead, going from here, you go straight to here. If you applied a natural log to both sides, you would still get to here, because remember, natural log undoes e. Then you need to go ahead and get t by itself. Right now, t is being multiplied by something, so all you'd have to do is divide. So you type this into your calculator, go natural log. It already gives you a parenthesis. You go 738, then hit divide, then 9, then close your parenthesis, then divide, and type in that 0.872. And when you do that, you get t to be about 5.0536 days. Now, I would probably just say that's really just basically 5 days. It's extremely close to that. Okay, now go ahead and read through this one. Now, in this case, we are dealing with a half-life. Once again, that's how long it takes for half of it to decompose, which means it's going down. And we're also dealing with this, which I would say is scientific, and it's going down in amount, so I would say we're going to be using this one here. So we'll go ahead and write that out. You know you're asked to find K, and then you're told some time here. Now, what about your initial amount? What about your final amount? They don't give you that. However, you could use whatever you wanted. If you use 10 here, this would be 5 over here, because whatever you start out with, you got to have half of it over there on the left side. Now, for me, I'm going to choose to start out with, say, 100%, which is 1 as a decimal, and then I'm going to end up with a half, or 0.5 over here. Now, on the right-hand side, I'm timesing by 1. Timesing by 1 doesn't really change it. So then I end up getting this. And then you're dealing with an e, so you definitely want to use natural logs. You could either use your definition of a natural log or apply a natural log to both sides. It would not make a difference. But either way, you would end up just getting this. Now, I'm choosing to go ahead and, since I have really 3 things, a -1, a k, and an 1800 multiplied together, I'm going to put the negative and the 1800 together. So then to get k totally by itself, to undo that multiplication, it's going to be natural log of 0.5 divided by -1800. And then you can just type that into your handy-dandy calculator, go natural log, 0.5, close your parenthesis, divided by -1800, and then you would end up getting k to be approximately -0.000385. A lot of times we don't have that many decimals, but we had so many zeros here before we got to any other normal numbers, so that's why I went farther out. So go ahead and take a look at this next problem here. We have a computer engineer with his salary. He gets a pay raise each year. We're wondering how long it's going to take before we get to 50,000. So we're definitely going up in value. I would say we're not dealing with anything scientific, so we're going to start out with growth for non-scientific. We know our R, but we have to change that into a decimal. We know our beginning value. We know our ending value. And then we are wondering how many years, so that would be our time. So we need to get the part with the exponent on it, which is this right here by itself. So we'd have to get rid of that 28,000. Right now it's being multiplied, so we'd have to go ahead and do a little bit of division. Now it's 50,000 divided by 28,000 equals, and this right here, I'm going to just do that in my head. I know if I add 1, it's just going to be this. Now, when you're looking at the left side, you could leave it like that, but I know that I can drop off some of these zeros that are the same top and bottom. And I get this. So now that I have my part with the exponent on one side by itself, I can use my definition of a logarithm. And so I'm going to go log of my base, 1.05, of that fraction is equal to t. But now for me to type it into my calculator, I need to use my change of base formula. So I'm going to go log of the top part in the parentheses of that fraction over the log of my base. Then I can go my normal log, log, type in 50 divided by 28, close parenthesis, divide, go log 1.05, close my parenthesis, type that in, and then it gives me approximate 11.884 years. So yes, you need to include your units, which you have to read in the context of your problem of what your units would be. Now, you could also say that it's approximately 12 years, because 11.88 is pretty close to 12, and you're looking at how many years, so that he'll be making 50,000. It's kind of hard to have an 11.88 year, so we just went to the nearest whole number, especially since it was close. And then we have one last problem that you can go ahead and read through. So if you've not read through it yet, please do so. One of our key words here is depreciates, which means it goes down in value. So we know it's going to be a decay. I would say we're dealing with just the value of something. I would say it's not scientific, so we're going to be using this basic one right here. We are wondering how long, that's going to be our time. And then we know that the initial value is this, so that's our A. We are looking at it going down to this value here, so that's going to be our Y. And then we have a rate. That's our R, but remember you have to change that into a decimal. Your decimal point's here, you got to move it 2 places to the left, so it's a 0.06. And then once again, our variable's in the exponent, so you got to get this part with the exponent. on one side by itself. And just to make it look a little bit better, I'm going to move this up so it looks more like the exponent. So there we go. So that means I need to go ahead and get rid of that 12,500. Right now, it is being multiplied right here. So I need to divide both sides by 12,500. So I'm going to have my 86 divided by 12,500 equals, now you can either leave it like this here, or I can do that in my head. You can do it either way. And if I do it correctly, there we go. So then, once again, looking at the left side, you could leave it as it is, but I know I can also drop off a couple of the zeros, so I'm going to go ahead and do that. So now I can go ahead and use my definition of a logarithm, since I got the part with the exponent on it on one side by itself. So I'm going to go log of my base, which is that 0.494 of that fraction, is equal to my exponent. That's using my definition of a logarithm. So now to type it into my calculator, I have to use my change of base formula. So I'm going to go log of that fraction divided by the log of that subscript base. And I'm going to type that into my handy dandy calculator, go log 86 divided by 125, close parenthesis, divide log 0.94. And when I do that, I get about 6.0439 years. Well, we're wondering how long it'll take, and that's pretty close to just 6 years. So I would say my final answer would just be 6 years.